thank you everybody for being here, for attending this session, this webinar. I'm just going to leave Borut, who is an expert user of our 3D system and also an expert bike fitter and also a PhD. So I will let him just start this webinar. That will be the first of many, I guess, and I hope. So Borut, it's all yours.
Okay, thank you, Fernando, and thank you to the entire STT team for inviting me to this webinar. And yeah, I see quite a lot of you guys. Very happy to see. That's very good. So today's topic is going to be about a little bit an overview of kinematic assessment in cycling. So it's a very broad area and it's kind of impossible to cover everything in 1 hour. So what I would like to pinpoint in this lecture today is basically a few details which are the prerequisite of the kinematic assessment. So how you should interpret the data from the scientific literature, how you should be carefully assessing when you're doing your own stuff in your laboratory, and so on. So basically, we're going to look at some of those things in today's lecture. I will also touch a little bit more on the applied side, which means basically what are the guidelines saying, what's the science saying based on how you could set up a bike as a bike fitter or as a consultant to a cyclist using just kinematics. So I would recommend that we leave questions to the end. So write it down, you can write it in the chat and then we can cover it at the end. So good. Right, so before we start, a little bit about myself. That's me on the left. Well, all three, that's me. That's how I started with cycling as a young kid. Continue racing on the international level in mountain biking and kind of ended up in the academia later on, but all kind of colored in cycling colors. I have a PhD in cycling biomechanics. I studied at the University of Birmingham, where my goal was basically to examine motor control ergonomics and biomechanics of cycling. For the last 3-4 years, I've been working very closely with a company called Absolute Black. You may know that they started with oval chain rings. We've continued with a few other products, and I'm now sort of a lead scientist there at the company, looking at the development of new products, testing them using very high technological approaches to study basically everything with developing new stuff now. I'm also a former assistant professor at the university, teaching similar stuff from biomechanics to sport performance. But most importantly, I am bike fitter, like a lot of you guys as well, and a cycling biomechanics optimization consultant to many recreational cyclists and a lot of Grand Tour winners, world champions, and so on. So working with the World Tour level itself. So quick introduction, let's continue. So how everything started, it's a very interesting point. Looking just scientific papers, there were a lot of papers published in the past, but when you study those papers into a little bit more detail, you actually realize that all the recommendations, all the books, everything was written going back to a single one source. And that one source was actually Italian Olympic Committee. Back in 1972, they published a handbook, a textbook for Olympic coaches about cycling. And one of the things they covered in that book was also how to set up a bike using some of the kinematical data. But when you dig in this data a little bit more deeper, it's quite shocking when you realize how they established those standards. And those standards, they actually set them up in a way that they invited a group of very fast cyclists, looked at around 20-year-old, and basically just said, so these guys are fast, let's see how they're sitting, and this is how you guys should set up your bikes. And I mean, okay, for 1972, all good, but nowadays you will still find some of the recommendations, some of the bike fitters that are following some of the standards using, for example, knee angle or knee pedal angle, knee over the pedal spindle, phenomena like that. They're still using now in 2023, which are dated back down to 1972. So Modern bike fit nowadays looks something like that. We have high technological cameras, we have real-time data acquisition, we have three-dimensional information about the cyclists, we can give them feedback, very accurate, and basically we can synchronize with a lot of systems together. That's all good, and well, it's available, commercially available. STT is one of the biggest and, in my opinion, by far the best producers of the motion capturing systems. And but without knowing what these cameras and this software is actually doing, it's kind of pointless using that. Why? Because when you're going to relate your data that you're going to measure using whatever system, it could be from a manual goniometer, Vicon, or STT, it need to have some of the links to the science you're referring to. So every piece of equipment, every measurement you take, it needs to have some sort of a background. And what we call this is accuracy, repeatability, and sensitivity. These are the three terms that need to be met in order to have your measurement in a way that we call valid. So that the measurement you're having is actually representing something. So what validity actually refers to is how accurately one method can measure what's intended to measure. So for example, if some research has high validity, that it means that it's going to produce results that correspond to real properties, characteristics, or variations in sort of a physical or a social world. So it's very important, whatever equipment you're going to be using, that it's valid. So we're going to look into this methodological aspect a little bit more into detail. And one of the things that's very important, that the measurement technology that you're using has high degree of accuracy. So we refer to two terms. One is accuracy and one is precision. So accuracy basically tells us to the degree to which one result of a measurement conforms to the correct value or standard. For example, accuracy of a scale, if we put exactly 1 kilogram on it, the readings on that scale will tell us how accurate the equipment is. And it's same with the cameras. So we need to have how accurately can one camera or multiple cameras integrated into a system can detect one point. Now, on the flip side, which is not the same, precision is independent of accuracy. That means that it's possible to be very precise, but not very accurate. So the best way to illustrate that is using the dartboards. So we can have low accuracy and low precision, which you can see here. So basically, every time we're shooting somewhere else, we're not accurate. So basically, we are aiming for the bullseye, so for the middle. Or we can have low accuracy and high precision. So basically, we're always aiming at the same point, but it's not very accurate. Or we can have high accuracy, but very low precision. So basically, there's still some variation in our measurements. Or we want to have both. And that's basically what you'd be streaming for. It's having high accuracy and high precision of that, of your system. So there are many sources of error. The sensors you're using, so the cameras, for example, or the any motion capturing system you're using is essentially how well it's developed and designed in order to detect the position of the markers, for example. Then we have our measurement setup. Have we calibrated our cameras, for example, optimally under the angle of 90 degrees, so we can really have a true three-dimensional information about a certain marker? And it's also the property of the object surface, what we're looking for, so the markers. If you can imagine, if you have like a very big marker, even though if we take the middle of it, the chance of having an error is small. Now, on the flip side, if I have a small marker, it's less likely that it's going to be detected by the motion capturing system. So going forward with this methodology, and I promise I'm going to stop after that, are reliability and sensitivity. So these are another two terms that we need to refer. Reliability, a similar result from day to day or trial to trial. So we know two different reliability. One is inter-session, one is intra-session. They're both equally important. For example, if I give you, you can have a very accurate system to detect, but then let's say you're measuring your knee angle, your cyclist, and you change absolutely nothing in that same trial, like he just repeats it, and that knee angle changes for 5 degrees. I'm exaggerating, but just to illustrate that. Or, for example, you measure one rider's position one day, and then you call them next day, and you have a different measurement. And that's called reliability of the measurement. And we want the whole measurement to be as reliable as possible. And that's not just up to the device or the technology you're using, it's also down to the human variability. There's skin movement, there's the placement of the markers, it could be some light artifacts. There's a lot of things that can affect this reliability, or often also called repeatability. Well, the last one, but also very important, is sensitivity. And sensitivity is basically an ability to detect small but significant or important changes in the measured value. For example, if we change the position or the angle, will our system detect this difference and actually be able to see there is a difference, for example, in two different seat heights. So these two terms, precision, accuracy, and reliability, sensitivity, basically gives us the total error of measurement. Now, the error of measurement can also be due to some other factors. It could be skin movement. So if you can imagine, we have some so-called guidelines or reference values based on bony landmarks. So every manufacturer of measurement equipment will probably give you indication where to position that marker. But if, for example, just touching your medial condyle, lateral condyle on the knee, when you have your knee flexed or extended, that is going to change. So if you're touching your skin, that skin's going to travel, and that's going to be changing. So you do have skin, and especially when cyclists are wearing clothes and they have soft tissue, we get those so-called soft tissue artifacts. Now, that's unavoidable. The only kind of possible way is basically to drill a hole into your bone and place a marker rigidly to the bone, which is not very ethical, or you're going to lose that client forever for sure. Joke aside, but how we can minimize that error is the most important thing. Now, I would suggest, and that's also how we do it, and a lot of the bike fitters is, that you position your, when you're placing your markers, you don't do it on a massage table, you don't do it when the rider is standing, you do them when they're on the bike, and you position their extremities, their legs, hands, and torso in a position where you're most interested to have the readings you're looking for. So for example, if one of the parameters that we're often using in bike fitting is knee angle at the bottom position of the pedal. So move the foot into the bottom position, try to replicate what's going to happen when the pedal, then locate your bony landmarks, and at that place you position the markers on the body. So that's one way to ensure. If there's a risk that you're going to be, that the markers will be falling off, what I would suggest also is basically to make a little mark. It could be one of those pens, skin pens that you can use, basically, if a marker falls down, that you correct. I've mentioned Lycra. Lycra will change when the rider will ride for another 5-10 minutes when they warm up. Just make sure that all the markers that you positioned at the beginning of the session are still corresponding to those bony landmarks that you're using in for the measurements. So there's another way which is also very convenient, well, not convenient, it's actually important that you do it, is basically to average your measurement. So when you, for example, recording 30 seconds of your knee angle, I'm going to use this example now in the future, you get something like that. So the knee angle is changing. but there is certain human variability present. So when you look at the peaks, for example, or the bottom, what you see is that some values are higher, some values are lower. This is completely normal. Humans, we're not robots. We're designed to have this human variability that's actually helping us in terms of sporting performance and just by living comfortably. But what every software should do, and this is actually a screenshot from the STT software, it should take a so-called ensemble average. So it should cut the cycles, all those cycles that we see, basically when the crank's traveling up and down, I mean in circles, should be cut and plotted one against each other on a scale from 0 to 360-degree crank cycle. So in cycling biomechanics, we're not plotting and we're not reading the data in respect to time, but we're most often plot all the data and we interpret the data, read this data in respect to the crank angle. And crank angle, best way is to go from the top dead center to bottom and back to the top. So 0 normally corresponds to the highest position when the crank is vertically pointed going upwards. Now, we did a study. I'm not going to show you with the boring data. An interesting way to detect what's the minimum number of cycles one should average in order to have a representative angle. It's actually quite low. It should be around between 7 and 15. Now, given that nowadays computers have a lot of memory and they're very optimized, you can store a lot more data. My suggestion would be once the rider is at a so-called steady state, so once they reach the dedicated power output cadence, they're sitting comfortably, not moving from the saddle anymore. When you start recording, record between 30 seconds to 1 minute. Even better is actually that you record 30 seconds and you repeat that 2 or 3 times. At least when you're establishing the baseline and the final position, confirm it. So it's like an experiment within the trial you're doing, just to make sure that the readings you're getting are not some artifact because the rider was not feeling comfortable on the ergometer, or maybe you changed the saddle and it's still looking for that position. Repeat the measurements 1, 2, 3 times, and once it's consistent, that means that your measurement is reliable and you can basically work on the change then to optimize or to make a change. So one is an assembled average, like an intra-trial averaging, and one is to basically average a few different trials and take the average value. So one paper that we published, that's almost 9 years ago, in Journal of Sport Sciences, we looked at the validity and reliability of different kinematics methods. So when I say kinematics, it's not just 3D fancy kinematics. Even just looking at the angle of the inclination, it's kinematics that as well. And back in the day, it was still popular to use the manual goniometer. It was popular to use some electronic goniometers. Then high-speed cameras were becoming popular, and 3D kinematics obviously was gaining its popularity back in the time. So we wanted to compare those methods for one most common parameter that bike fitters are using, and that's the knee angle at the bottom dead center. So this is basically the image here you can see. It's how we were measuring the knee angle, and we've measured 3 different saddle heights which corresponded to different knee angles. So it gets quite complicated, but at the same time it's simple. We've set the position up based on a manual goniometer. So we used a manual goniometer. We've measured the position here using the same bony landmarks where we've placed the Vicon markers on, and we've set 3 positions. One was 25, 30, and 35-degree knee angle measured in a biomechanical way. And then we recorded basically that dynamically using the 2-dimensional high-speed camera, then a 3D Vicon camera, which was at the time state-of-the-art, was 13 cameras, and it's very, very accurate and reliable. And we used an electrogoniometer. So what I want to show you is basically there's a difference between every single method you're using during the same trial, using basically at the same time, just acquiring with different systems. Now, one that you should neglect immediately, you see that's the electrogoniometer. I don't think there's a single bike fitter in the world that's using it. It's more for clinical work when you're doing simple, slow, isolated movements. So it's got a lot of muscle movement and everything that cause the artifacts. But what's interesting is if you look at those yellowish lines, these represent the manual goniometer readings. And the differences between, for example, a 3D measurement and a manual goniometer is huge. And that's very important when we're looking at scientific data. Some other research done actually not so recently, about 5-6 years ago, by Wendy Holliday and Jeroen Swart, actually showed that manual goniometer, it's very reliable measurement. But what's important that it's different to 3D kinematics. So what you're using, you cannot then read scientific information by XY scientists showing that this angle using 3D kinematics will reduce the load on the knee, and then you will just copy that information and use it in your practice using a manual goniometer. Unfortunately, it doesn't work that way. So that's why it's very important that whatever system you're using, you need to know the limitations and the methodological characteristics, and then make the correction if it's necessary. So another thing which I would like to pinpoint here is the parallax error. So when the 2D camera is measuring wider apart, the bigger the error. So the center position is actually quite accurate when you're looking in a sagittal plane. The moment you have a little bit of a three-dimensional movement, for example, knee traveling left and right, you will have some error. And you can actually see that on the high and low position, there was a bigger error, whereas at some mid positions or third degree, the difference between 2D and 3D was actually neglectable and not statistically significant as in this position here. Yeah. So at the same time, we also measured the intersession reliability, and basically all three systems, 2D camera, 3D Vicon, and electrogoniometer, showed they were quite reliable. So there was trial 1 and 2 with minimum difference. So high reliability for every single system, but the accuracy was a lot different to those. So that's one aspect when you use the different technology. Another aspect in kinematics assessment is the setup you're using. And a very good paper of the before mentioned research group, Wendy and Jeroen from South Africa, they examined how a workload would actually affect your readings. And it showed that it's actually quite significantly different when you're looking at 60, 80, and 90% of the maximum power, or maximum heart rate. And there was difference in, if you look at those numbers here, everywhere you see those signals, it means that there was a statistically significant difference between or among those different workloads. It begs a question, so what workload one should be used during a bike fit? At one point, the workload should not be too low because it doesn't really reflect what the rider is using during outdoor. And at the same time, you don't want to go too high because you're risking the onset of fatigue. Because once the rider will get fatigued and will start changing the pedaling technique, it means that you're again measuring some errors which doesn't really reflect the rider. So I'd say sweet spot, every rider will have a different one, and just stick to that one. My opinion, what I do is at the end of the session, we always test the position at high workload. It's good indication for them to feel how it is when you have to push a little bit harder, but you also look if there's any massive change, any substantial change in kinematics or other parameters you're measuring when you add more workload to that. So this was a little bit of a background on what you should be methodologically careful about when you're looking at the kinematics during cycling. Now, the practical part of it is bike fitting and how you can use 3D kinematics. I'm only going to look at some of the data I've kind of collected from a lot of information out there. If we would want to read a lot more and cover a lot more, we would need a day or two workshop just to basically go through every single study and look how it is. So bike fitting, first of all, we need to ask ourselves, what's the point of a bike fit? And when we're speaking performance-wise, the aim is to maximize the effective force application and minimize all the resistive forces. And we can do that. We can change the paddling technique. We can change body position. We can modify the equipment. A lot of things can happen, but basically, when a rider is riding outdoors, one needs to overcome all the resistive forces. And those are the aero drag, which is the dominant resistive force during cycling when you're going fast or on flat. Then we have the gravitational force, which is more important when we're going uphill. And then we have some frictional losses of our drivetrain, and we have some frictional losses between the tires and the surface on which we're riding. And our force that we generate basically needs to be bigger than all those resistive forces. And how do we accomplish that? Well, by pushing on the pedals, yeah? And that can happen in various directions. So bike fittings aim should be to basically be as effective as possible, to use as little energy as possible, and being able to develop the highest possible force to go as fast as possible. Now, in this talk, I'm also going to be referring to some of the effectiveness, efficiency terminology, and I'd like to clear that before we start. One is a metabolic index, and it's called efficiency. Mechanical efficiency, there are different mentions. It basically refers to the energy consumption or how much energy you use for a given workload. Whereas that we have a mechanical effectiveness, it's purely about the force. So what percentage of the force that you push on the pedals actually goes into power. And that's the part which we'll spend more time today, because it's also in a way easier to measure, more biomechanically measure. So joint angles. First of all, again, going into scientific literature, a lot's been done, and then a lot of manufacturers followed using those parameters and defined so-called joint angles. And one of the most common in past, which I think is wrong, was using the knee angle and the hip angle and the shoulder angle as illustrated here. So the greater trochanter, the acromion, epicondyle, lateral condyle, malleole, and basically detecting and showing those angles. However, recent research, a lot of those angles, especially the hip and shoulder, are not really the angle of the shoulder and the angle of the hip. So the new way, and which I think the only way, correct way, is to calculate the joint angle based on the pelvis orientation. So with here, if you put one marker at the S1 and one over there where basically it kind of bends a little bit, you will get the real hip angle. And at the same time, you will look at the upper thoracic spine and the shoulder angle from the acromion to the epicondyle, and that gives you the real angle of the shoulder. So again, Jeroen Swart and Wendy Holiday, they've dedicated a lot of energy to spread that information, and some of the manufacturers, including STT, when they calculate the values, these are the values you're looking at, and these actually correspond and represent angles that you should be using when you're doing the changes. So a little bit of an overview of research, how different saddle height and what the readings on the knee angle reflect performance. In this case, Bini have done some of the research in Australia, looking at different knee angles and then measuring index of effectiveness. So basically how effective your pedaling stroke is. And they showed that 25-degree knee angle it produces more efficiency, more effectiveness than higher knee angles, which correspond to lower seat heights. So the smaller the number in this case, because the knee angle was measured in a biomechanical way, as illustrated here on the photo, the higher the seat height is. They also split the group between cyclists and triathletes. Now, this particular population, cyclists and triathletes, are not different just in the outfit they're using and the bikes. They're also different that triathletes do other sports as well apart from just riding. They have to run and they have to swim. And what's common to swimming and running is what you do with your ankle. In running, you need strong calves, so you gain strength in your calf muscles. And in swimming, you actually have to do a lot of plantar flexion to basically improve your kick with the foot to propel through the water. So they looked at a little bit further into this. Why do triathletes exhibit higher index of effectiveness compared to cyclists? And when they looked at, for example, what's happening at the ankle, they saw that the mean angle, so the position of the foot respect to the horizontal, it's a lot more in plantar flexed position than triathletes. So you see the black values here are bigger than the gray ones, which correspond to cyclists. At the same time, they looked at the range of motion through the pedal stroke. And triathletes, they tend to have less range of motion in the ankle than cyclists. So basically, cyclists tend to use a lot more of that so-called ankling technique when they're dropping the heel during the push and then pulling it back up. But that actually exhibited in that their paddling stroke was less effective than the corresponding than triathletes who were more effective using stiff ankle and keeping the foot in more plantar flexed position. So this is one research out of many, which I took out for them to present how you can use kinematics to set up the bike using really knee angle and ankle angles and looking and trying to improve that. I will refer a little bit more to the ankle angle and the foot angle a little bit later on with some other research that we've done in-house here in Slovenia. So the other thing which is very interesting, you as bike fitters, I assume majority of you are working with cyclists. There's a lot of low back pain during cycling. And one of the things how you could use kinematics, and in that case, because it's a little bit more statical measurement, it doesn't need to be a fancy equipment. It could be an inclinometer, it could be a goniometer, any of the equipment you're going to be using, looking at the lumbar kinematics. And this research from about 10 years ago looked at how much time you spent in your lumbar flexion throughout the 2-hour trial. So they invited 2 types of cyclists, those with low back pain and those that were asymptomatic, so non-low back pain. And they asked them to ride the given workload for 2 hours on a turbo trainer. While they were doing that, they measured the degree of the lumbar flexion. So initially, they measured with a trained physiotherapist and actively followed them to the maximum lumbar flexion they can achieve. And then they looked at the percentage of the total lower lumbar flexion during the trials. And you can see there's a big difference between cyclists, between low back pain patients, those are the black lines. They have a lot more lumbar flexion than cyclists during that 2-hour trial. At the same time, when you look at the time they've spent in the total lower lumbar flexion, that the low back pain patients had spent a lot more time having their lumbar spine flexed compared to the no low back pain. Now, as I said, it's quite an easy measurement. I'm sure a lot of you are using that just observational technique, looking at the angle or just observing what you do with the pelvis, what you do with the lumbar part of the spine. But this is how you can use the kinematics. Again, STT is doing great job here. It's a lot of markers on the spine that gives you all the values in real time, so you can even teach the riders basically if you cannot achieve your goal with the position itself. You can use biofeedback and teach them how to sit, how to rotate the pelvis in order to reduce the load on the spine and to reduce the low back pain. So another thing. Okay, so moving forward, and the last chapter of today's lecture is how we can use our foot angle, again, pure kinematics, to improve your paddling technique. Now, before we go to paddling technique, how do we even assess paddling technique? What equipment we should use? And it all started again in 1981. They developed those interesting paddles with using piezoelectric sensors, and they were actually able to detect three-dimensional forces on the paddles. Now, the big problem back then was this computer back there, and it had a lot smaller memory than the computers nowadays. So their memory ran out after one complete paddle stroke was recorded. So you can imagine, in order to get a reliable measurements of hundreds of cycles, they had to change the memory many times and analyze by hand. But it was a good start, and that start continued. Now, my specialty, my personal specialty, is actually in force measurement, because I used to work in a company where we were developing a new sensor, and this is how our development looked like. The first prototype, a little bit more advanced, connected to a little bit stronger computer than back in 1981, so we were able to detect a lot of forces. So we started with 2 dimensions, continued with 3 dimensions, and ended up with a 6-component sensor, 6 prototype. Now, at the end, we were able to achieve a product that was that's now used worldwide by a few university research institutes and some of the bike fitters, including myself. It's a wireless sensor that's able to detect 3D forces and 3-dimensional torques on the pedals in real time, wirelessly, at a very, very high frequency. So, looking at the pedal forces, why they are important. If we have all this information which I measured, so the 3-dimensional forces, the vertical, the anterior posterior, and the medial lateral, please do not neglect this one, because it's very important, even though it doesn't contribute to pedaling. And at the same time, we can measure crank angle and pedal angle. We can do some mathematics. We can get out first the resultant force, and that's the total force. So regardless of the direction we're pushing, even if it's side or pulling, the resultant force will react. But what's actually pushing us forward is the effective force. So that's the force, that the component of that force that goes vertically to the crank, perpendicular to the crank. And once we have all this information that you see on the screen right now, we can calculate torque, which is essentially effective force times the crank arm length. And we can calculate the power output, because we have the crank angular velocity in radians. Now, bear in mind, this is very important to measure in real time, not just to calculate cadence and make an assumption that the crank velocity is consistent throughout the crank cycle. It's not. It's changing. There's variability, and that's why you get sort of a sinusoidal look. And we end up with something what is here in the middle, and that's our basically how we pedal. So this is push down. We achieve the highest force somewhere around 110 degrees of the crank cycle, and then it's slowly moving back. Now, one thing that you notice, that the arrows here are actually pointing in the opposite direction. This is completely normal unless you're actively pulling up and spending a lot more energy and putting strain on your joint. You're actually not contributing much to pedaling. Now, apologies for the Slovenian language. I will translate this. This was a little bit of oversight. We split these forces into 2 subcomponents. One is the non-muscular subcomponent, and on the right side, we have muscular component. And let's first spend some time here. If you look at the biggest muscle contribution, actually comes a little bit earlier in the crank cycle than what you see here as the result. And basically that corresponds to the human biology, how we're actually directing our force. And at this point, humans were designed to push the most, and that's why we see the highest reading here. But we cannot neglect the non-muscular component. Weight of the leg, which is the left one, and that's going to be pretty much equal throughout the crank cycle, always reacting in the direction of the gravity. And one thing that's very important, it's called inertia. And then the inertia, once you combine all those components, the weight of the leg, the inertia, and the muscular subcomponent, then you get something like that. And that's the output. And that's the output that's important, not separating weight of the leg, inertia, and muscle, but the output. And that's what we're optimizing. So at the end, it comes to something like that. Again, from 0 to 360, we get our total force, the solid black line. We reach our peak somewhere between 90 and 110, depends how we measure it. And it's always a positive value. Now, this thin line represents the effective force. And the effective force is the biggest, around 90 degrees. And everything you see here white, we called energy lost. So basically all that is wasted. And now why this is important, if you look at the so-called wisdom, our metabolic system is analogous to sort of a locomotive engine on a steam train. So it fuels the body's ability to generate the force. So the greater the force we need to require to be generated, the harder the engine needs to work. So we want to minimize the waste of the force in order to save energy. So what's optimal pedaling technique? Preventing excessive dorsiflexion is something that we're actually going to dedicate a lot of attention today. There's been a lot of research done on pulling up, pedaling in circles, and every single one of those research showed that the moment you start changing your pedaling technique in the upstroke, you're spending a lot more energy and you're actually dropping your performance. So for a steady state cycling, don't think about sprint at this point or very short bursts of high intensity exercise, but on a steady state conditions, you don't want to pull or pedal in circuit. But what you can focus is your downstroke. That's where the majority of the force is generated. That's where the majority of the power is being generated. So we looked at what about if we prevent dorsiflexion, so we prevent dropping the heel, keeping your stiff ankle, and be as strong as possible during the downstroke. And in Canon and colleagues looked at pedaling that and basically showed that energy consumption is lower in plantar flex position compared to the dorsiflex position. So when they prevent falling, dropping the heel, they saw there was a save in the energy. Vinny, the research we mentioned before, triathletes had less of the range of motion in the ankle, stiffer ankle joint, and they showed they also found to be more effective. So observations from practice, a lot of people actually claim when they have a rigid lever, preventing a backward tilt of the pedal often results in increased pedaling effectiveness. So what if we provide training with the visual feedback and see how that's changing? So that was our study. Using the technology I mentioned before, we displayed in real time pedal angle. Here you can see, so that's left and right, and in both cases, this is the direction you're pushing. So this is the knee angle that was displayed at the same time when they were pedaling. And we said, right, there's a control condition. You can ride in any way you want on, and you can also pedal with preventing the backward tilt. And the results were shockingly positive for the plantar flexed condition. So plantar flexed, this is here, index of effectiveness across the entire pedal stroke was almost 100% higher than in dorsiflex condition, whereas the one I think is most important is the index of effectiveness of the downstroke. And 65% compared to 56, the difference is massive. It's like 9% difference. And that was actually correspondent by oxygen consumption. You see, was a little bit of a difference, and the ventilation VO2 equivalent, ventilatory equivalent, which at the time was this intensity is considered a sort of a metabolic standard. So the lower it is, the more energy you save. And you see there was a statistically significant difference in that as well. Pedal angle was quite substantially different. So when we looked at the minimum pedal angle, this was almost horizontal or 20% back heel drop. So how you could use kinematics. Very simply, look at the planar, the sagittal plane, and try to prevent the heel drop. Now, this can be achieved with bike fitting. So if you set the position in a way that basically you're physically impossible to drop the heel during the downstroke, or simply by giving feedback, biofeedback. You could use your eyes, or you could use a camera, you could use STT system giving feedback, and will improve the performance. So as the take-home message, read, study scientific papers, but assess the methodology used very carefully. Don't directly go back to your practice with the same numbers you've read. First, look at what equipment they're using, what equipment you're using, and try to see if you could basically use the same values. Don't focus on one collective variable, just one, and this is how you set the bike, but use a comprehensive approach, study other variables as well, look at basically all planes and all different things. And be aware of the measurement error of every single thing you measure. So that's from the official side. Everything. Thank you very much, and I'm open for questions now. There's also a chat I think you guys can use that I see now. You can write the question or... Okay, Armando.
Yes, I'm sorry about my little English, but do you have a study that when you compare the crank arms 165 from 170 in triathletes bike fitting?
Yes, very good question. There's been a lot of research done in past, not just 165 to 170. There was some research done even with 145, 155, and so on. And it's very interestingly, basically, that shorter crank arms in triathletes or road cyclists, shorter triathletes actually favorable in all aspects of cycling performance except one, and that one is standing start, which is completely irrelevant unless you're a BMX rider at the start gate. So shorter crank arms, open the hip, you can set your position a lot more aerodynamically without taking any risk of losing power output. And interestingly, like every single research I've read, every single research I've done in the lab, because we've done a lot of on knee loading more from the rehabilitation aspect, which is not directly the question you're having, but is actually favorable to go down to 165, 160, even 155. And interestingly, when you're looking at the new Shimano group sets with the 12 speed ones, Shimano actually follows that philosophy now, and you can get high-end equipment in 160, which wasn't possible before by OEM manufacturers. So I'm sure if you're going to look on PubMed, Jim Martin did a lot of research on power output, economy, etc., using different crank lengths. The only thing I want to mention regarding crank lengths is that I think it takes some time to adapt in order to detect difference also from the power point of view. That was my observation from some of the case studies we've done.
Thank you. Just one more doubt here. When you are adjusting the cleats on the cycle shoes, we have two kinds of with two types of feet. We have Graecian feet and the Egyptian feet. It means that you have a medium metatarsal point different for each feet. Do you have any study about that?
Cleat is very sensitive area, and there's been a lot done looking at biomechanical variables, and if I remember correctly, regardless how you position your cleats, it doesn't really matter. There is, however, something, I don't know if it's published, but we've done that in Birmingham. Well, a colleague of mine, Xavier Disley, done that using so-called floating pedals. So the pedals were actually able to move freely left and right, and they were able to rotate 360 degrees freely. And when they were actually looking at the Q factor, but regardless of that, what they found is after a few minutes of riding on those floating pedals, they realized that at some point you stabilize at the position that you prefer the most. And when they were following up with the measurements after that, fixing the positions, everything that was away from your preferred position was less beneficial and was a lot more energy expenditure, and also biomechanically speaking was better. So basically, whatever fits the fit and the whole kinetic chain best, that was found best. And this is also the philosophy I'm pursuing as a bike fitter, except I'm not using floating pedals, I'm using force pedals measuring torque. And I want to minimize the torque that's happening rotationally, so around the z-axis, and also the torque regarding the lateral torque, how much you're pronating and supinating. So I don't set up based on how I see the fit, but we set the cleats basically that the output at the end is as centered as possible.
Thanks, Borut. I think there's another question coming from Marcus, who says in the chat, do you consider and or determine the center of gravity of the rider on the bike during the fitting process? If so, how without the pressure mapping? If I may answer that a little bit, because I know that, I mean, at least with our system, we do it based on the marker positions. So we are, of course, having some assumptions on the way that we are providing to the segments. Of course, it's a generalization. It's not, but it's an estimation. So when you determine, or where we as STT determine the center of gravity, at least we tend to say that it is not important. It is not as important where that center of gravity is in the 3D space, because it cannot be accurate, for example, because we don't take into account the head, for example, we don't have markers in the head. But what is interesting is to see the variation of that center of gravity. If that center of gravity is stable in the 3 planes, I think that is interesting to see, at least with our system. But what do you think about that, Borut?
So yes, it's basically what I wanted to mention. I actually prefer the way Kinematics are giving us the center of gravity, and I'm looking at it in relation to the bottom bracket. So it's very important, especially with clients that are experiencing, for example, too much loading on the hands, or they have any neuropathies in the hands, or a lot of things can happen when there's too much loading on the upper extremity. In that case, we always look at the center of the gravity in relation to the bottom bracket, and we position that, and we can change that basically using the saddle position, moving backwards, or the whole cockpit direction to move the center of gravity more backwards.
Okay, we have another question, or Instagram.
What crank length Pug is using? That's top secret.
That's secret, yeah. There's another one. Is the ankle angling may change if you're able to copse positive till 100 millimeters as a triathlete?
Yes, basically, I mean, the entire lower extremity is connected, and you change one thing, it can result in a different way. So just by moving the position of the seat fore and aft, and triathletes, yes, tend to sit a lot to the fore, the knee over pedal spindle changes. But what's important in that case, that the entire force profile rotates forward. So your maximum position of the angle of the crank where you exhibit maximum force is also moved forward a little bit. So it's very important that you don't stick to the knee over the pedal spindle as solidly in that case, but you use it also in terms of where you are sitting and where the maximum force is happening.
Mm-hmm. Okay, very interesting. Let me see if we have any other question in Instagram. If not, you already have there Borut's email, his contact, so that in the case there's any further questions, I'm sure he will be glad to answer them to you later. As we have said in the beginning of the webinar, we will be uploading this also to our YouTube channel. So well, if there's no other question, I will only want to say thank you to Borut. It has been a pleasure to having you here, and also to the rest of you. We will be glad to help you if you have any question with the system. If you want to know a little bit more about biomechanics, here is also Borut. We will be presenting new webinars throughout the years during the year. So keep posted to our social media. And thank you all.
Thank you, guys, again, and happy to hear from you.
Okay, bye-bye. Have a nice
Bye-bye.
day, everybody. Bye.